Hi there. Today I'm presenting on my Optoelectronics and Optical Communication assignments, subject code ETM4006, and my name is Muhammad Firdaus bin Sharif, and my student ID number is 113112316, and my lecturer are Professor Dr. Wong Ang Kiong, and my assignment is review on the state of the art, latest technology, wavelength division multiplexing, optical communication system. And then we proceed to the very basic of the wavelength division multiplexing, where WDM is categorized in the basic block diagram. That is multiplexer and demultiplexer at each of the end of the fiber, where on the multiplexer, the multiplexer is a number of carrier signal onto single fiber using different wavelength. And then the wavelength division multiplexing can be defined as a one-line fiber, and then it also can be a bidirectional communications. And wavelength division multiplexing also can be a multiplication of capacity, and it also has the multiplexer that can be functioned as the joint signal, and then the demultiplexer at the end of the fiber can split the signal. And as what that I can understand on this topic is on the multiplexer side, on the yellow rectangular table, there is the combination of multiple signal on different wavelength that is combined into one and is passed through onto the optical fiber that is circular one. The optical fiber is act as a passing point until it reach the destination, and then it reach the point of the demultiplexer, where the demultiplexer splits the signal again into each respective wavelength, and each respective wavelength are being distributed into the destination. And the wavelength division multiplexing, it can be categorized into many different types. One is CWDM, or conventional or coarse WDM, and the other is DWDM or dense WDM, and also what I have seen other is time division multiplexing, and also I think that's it. And then for the basic configuration of the wavelength division multiplexing is it can be categorized into two types, and one is one-way transmission, while it requires multiplexer and demultiplexer, where the figure shows the multiplexer and the demultiplexer, and between the multi and the demultiplexer there is optical fiber. And for the two-way transmission, it only requires the multiplexer or the demultiplexer at each of the end. So between the optical fiber, there is only need of one device that act as both. There is multiplexer and demultiplexer at each of the end. And then for the wavelength division multiplexing, the disadvantages is the transmission capacity is increased per fiber. That means the data rate also become bigger, and then it has less propagation delay, and it also reduce the cost reduction, and it also has simultaneous transmission of different modulation scheme signals, and it also has service channel expandability after fiber installation, and it also has low bit error or BER. And the the item necessary for the wavelength division multiplexing there is three. One is optical fiber, second is light sources, and the third is photo detectors. And of what we can see from the wavelength division multiplexing system design, there is one component that is act as a state of the art or technology that can be evolved from time to time, and that device is called optical multi or demultiplexer. From this device, optical multi or demultiplexer, this device acts as a base that can be evolutionized, or it can be combined, or it can be hybrid in between the other device, and it can be used as a scheme or combined device to make the data rate and the capacity bigger from time to time. And from this figure, we can see a block diagram that I can show to you guys that also act as the optical multi or demultiplexer, where we can see the first multi or demultiplexer block diagram here. It can be diverged into two types, wavelength selective and wavelength non-selective. And then we focus on the wavelength selective, where the device that I want to focus is the passive type. The passive type is come from the wavelength subjective, and inside the passive type there is four devices of optical multiplexer or demultiplexer. The four type is first is angular dispersive, and the second one is dielectric thin film, and the third type is hybrid, and the fourth type is planar waveguide. And the one that I want to focus is the angular dispersive, because on the assignment, our professor want us to focus on the state of the art of the WDM technology, and our professor want us to focus on the devices or the technology that enables the high bit data rate. And from the reference that I inspect and what I can see, the devices that enable the high bit data rate is from the angular dispersive. And from angular dispersive, it can be categorized into two types. One is grating and one is prism. And what I want to emphasize here is the grating type. The grating type, there is three types, but only two types that what I can see that emphasize the high bit data rate. There is first the litho type, and second is the third type. The litho type consists of conventional lens type, and the second one is the green rod lens type. And for the second devices that emphasize the high bit data rate is the third type, that is consists of concave type, and the second one is slab guide type. Okay, here is where the optical multi or demultiplexer devices that the state of the art technology, and there here is the litho type that what I can see from the reference is it can enable the high bit data rate. So the litho type consists of two. There is the one we introduced earlier. One is conventional lens type, and this is the block diagram. And the second one is green rod lens type. And from what I can see, the green rod lens type is superior than the conventional lens type in the compactness and the ease of alignment. And here we discuss more on the green road lens type. The green road lens type, and this is the figure here. And the operating principle are the input are collimated by lens and reach the diffraction grating here, and the light angular dispersed according to different wavelength and reflected at the same time. And the different wavelength pass through the lens and also focus to output fiber at the same time. And each wavelength are fed to individual detector at the output. And this is the multiplexing characteristic of electrotypes, where the sample here there is 5 channel, and from the 5 channel we must find the differential or the difference of the diameter. First is the difference of the diameter comes from the input fiber. First one is the core diameter, and the second one is the output fiber, the output core fiber. And from the output and input core fiber diameter, we can find the difference in the diameter, and the difference of lambda and the difference of z are the dispersion focalization, I think. And the dispersion focalization we can find from the characteristic of electrotype. There is one that I haven't touched it, that I haven't read it through. And from the value that all that have been inserted, we can find the bandwidth. The bandwidth can be found from the formula here, and the demultiplexing parameters performance we can show here. There is number of channels from 3 to 20 channels, and the insertion loss is between 1 to 4 dB, and the wavelength spacing are between 20 to 40 nanometer, and the crosstalk attenuation is between 20 to 30 dB. And the other type that I want to talk here is the third type aside from the electrotype, and this figure is the third type. Here is the fiber array, the guiding type, and here is the concave diffraction grating and the multi-mode slab waveguide. The one that difference the third type from the electrotype are the third type have no lens, but the operating principle is similar to electrotype, but the third type during the operating principle it act as a lens, although it have no lens. And the third type categorized into two types. One is concave grating, and the other one is slab waveguide plus the concave grating. And the performance of the third type is almost similar to electro, but are not have adequate passband loss. And this one is the reference that I got, the review and status of wavelength division multiplexing technology and its application on year 1984. And that's it. Thank you guys.